Thank you, Carsten, and hi, everyone. So actually following in the same theme of biometrics, and specifically with respect to face biometrics, I'm going to be talking about the work we've been doing, looking at investigating the fairness in commercial face recognition algorithms. So let's get started. So I just want to say that the slides were structured in a bit of a generic way, but considering the expertise of the audience here, I will be kind of skipping through the first section and spending more time on the results we have, and what is our aim of our investigation, so that we have more than enough time to get some feedback, which is really what I'm looking forward to, and I'm quite excited to hear what people have to say on this. Right. So of course, within face recognition here, and just simply highlighting the fact that we have two primary modes. So you have a verification mode, which is probably what the first two speakers have have highlighted, where there's a one-to-one match between to verify whether this particular person is indeed the one they're claiming. But we also have an identification mode, where you try to identify, based on a known set of identities, who is this person who is in front of you, for example. So what are our key research questions we are interested to answer? So in both the verification and identification use cases of face recognition, we would like to evaluate the fairness with respect to gender and race features across all of the different commercial open source, actually open source face recognition algorithms that we have available to experiment with. And when we talk about fairness, we clearly define two specific criteria for fairness. So a specific homogeneity criteria is let's say a less strict criteria for fairness, which ensures that there is within group fairness. So what do we mean by within group fairness? It basically means that the average similarity between different any random pair of individuals within the same group is equal to the average similarities within a pair of individuals in other groups as well. So for example, the average similarity that we get from the algorithm when we compare two random, let's say, Black females, should be equal to the average similarity of two white females. This ensures that the chance of you misidentifying a Black female as another Black female is same across these two groups. Whereas broad homogeneity is a much more, I would say, harsher or stricter condition or criteria for fairness, where you also expect fairness between the different groups. Okay, so as an example here, like we spoke about the average similarity between, let's say, two pairs of Black females. Now we expect that to be equal to also the average similarity between a randomly chosen Black female and a white female. So as you can possibly imagine, that this is much more harder to achieve a broad homogeneity from the output of an algorithm. Okay, so what is our research strategy into how we are going to investigate fairness? So this starts with, of course, identifying a data set that has manually annotated gender and race labels, so that it is suitable for this kind of evaluation, so that we avoid using another algorithm itself to get these labels, right? So, and considering how all of these algorithms are really working on the same kind of deep neural network based architecture to get you identity labels or gender labels, then we don't want that to what do you say, let's say, skew our experimental design. Second thing, what we want to do is we want to first establish that your off-the-shelf pre-trained facial recognition algorithms to establish whether there is indeed a bias in them by using them as it is. And once we establish that there is a bias, which we have done, as you will see shortly, what we then want to do is we want to investigate what is the source of this bias. And one of the key kind of, let's say, hypothesis we want to test is that does the composition of, let's say, gender and race proportions in the training data, does it change the resulting bias from these models? And once we kind of get more idea and kind of are able to quantify the impact of, let's say, training data on bias, we would like to make certain recommendations for how we can make these algorithms fairer. So some of the key, let's say, potential recommendations we have identified maybe something like, what would having a balanced set of training data across gender and race groups, and potentially even having a, publishing a shareable recommended data set that we think fairer models can be built on. A second thing would be potentially explore the possibility of requiring an ensemble of models that are built separately for each group to ensure that we get at least a broad specific homogeneity criteria met. And finally, with respect to setting of thresholds, which has already been highlighted in the literature as one of a challenging decisions to be made with respect to specifically with verification, like what is the ideal way to choose a threshold. So do we perhaps need these thresholds to vary across different groups to ensure that we are able to meet the fairness criteria? Okay, so this is possibly the last slide as part of my introduction. So here I just want to kind of highlight how a facial recognition, what are the different components within a facial recognition pipeline, in this case with respect to an identification use case. So it's not just about, just presenting an image to a to an algorithm and then it tells you an yes or no answer. There is a number of key components where you have different choices and decisions to make about how you want to do that. So starting with, when the raw image is presented, the first component is the face detection part. So you have a number of algorithms that do this. You also have a slightly, let's say, less complicated step of face alignment based on the features that are detected of the face and its boundaries. There is an alignment step. And finally, you have the extraction of features from the detected and aligned face. So this is where your, let's say, the most complicated deep network architectures are working to extract features. So now once you have extracted features and you also have a database of existing identities and their corresponding features, now these features are compared with the identity, the existing features of known identities, and a measure of similarity is calculated by looking at these feature pairs, and using which you make a decision whether who is this person that is being present. So I'm going to skip through the next couple of slides, which just goes into a little bit of details about what are the steps within the process. But I'm going to stop here, or pause here rather, to say that your typical model architecture. I'm taking the example of this VGG16 architecture developed by some folks at the University of Oxford. So you have of course, a deep architecture where you have a number of convolutional blocks within them, followed by potentially a more, let's say, just a fully connected layers that you see as flat layers over here. Now, the key point I want to highlight here is that most of these off-the-shelf commercial algorithms were originally built for and trained to output as a classifier of identities. So the goal of these algorithms were, if you were presented with a human face, the goal was to classify among the, let's say, the specified different specified number of identities, what which identity does this which class does this new image fall under? So our argument is that using these classifiers off the shelf is not ideal when we want to do identification, because identification, or even verification for that matter, is based on capturing similarity rather than classifying identities directly, right? So the key challenge that we have is we need to tune these models using a triplet loss function. So this is a loss function that enables us to extract feature vectors, which can then be consumed to measure similarity between pairs of images or individuals. Okay, and once we are able to do that, we can look at the similarities across these different race and gender groups to then have a more precise investigation into if there is bias between the different groups. So I briefly mentioned about how a triplet loss function is used to kind of adapt these classifiers into now something that gives us a measure of similarity. So the basic idea is that instead of training it on single images, you train these models using triplets of images, where the first two images, labeled basically the anchor and positive, belong to the same individual. And then you have a third image in the triplet, which is labeled as a negative image, which is an image that is different to the identity of the anchor and positive. And what you are asking the model to learn is that you want the model to output feature vectors for each image such that the distance between those feature vectors for the anchor and positive images are minimized, as while the distance between the anchor and negative feature vectors are maximized. So this is the kind of the basic idea behind using this triplet loss function, and it was originally proposed for this with this FaceNet model developed by Google, and it can be used to even retune other models which were originally built for classifiers to now give us the similarity measure that we are looking for. So what kind of experiments have we done as of now? So we have used this VGG phase 2 data set. So this is a publicly available data set that contains labels for each image's identity, gender, as well as race. So it's perfectly suitable for the study that we want to make. It covers a large diversity, but there is a possible limitation due to the fact that these are well-known or celebrity identities. So there may be a bias due to effects from makeup and lighting, etc. So if you look at the table here on the left bottom, these are the total number of identities that we have in the data set. We have about 9,000 odd identities, and the total number of images is approximately about 3 million. So you have a large number of images for each identity. But as you can see, the overall data set is quite imbalanced with respect to race and gender categories. So what we do is that among this whole data set, we are taking a subset of subjects that we take to create a validation set on which all our investigation of bias will be conducted. So we take an even proportion across all gender and race groups. And for each of these 100 identities, we have 10 images randomly chosen for each subject, which will form our complete validation set. So in total, we have 800 different identities and 10 images. So totally 8,000 images that will be used for our experiments. And all of the other images from all of the other identities outside this validation that are there in the data set can be used in whatever way to improve the off-the-shelf models. So what do we do with this validation set? So we have specified a simple framework using which we can do validation, or in other words, investigation into the bias. So this is specific to the identification use case within face recognition. So the validation works as follows. What we do is that we randomly pick one image for each of the different unique identities that we have in the validation set to create a reference set. Right? So this will be a database of reference images that we have for each identity, and all of the other 9 images that are left over for each individual forms our presentation set. And what is the idea? We basically ask the model to output the features for all of these images in our validation set. And then what we do is for each image in the presentation set, we calculate the distance between that image or the feature vector generated from that image with each of the feature vectors of all of the identities in our reference set. And the idea is that once we calculate these differences, the identity of the reference image that has the shortest distance with the presented image is the predicted identity of the presentation image. Now, the key assumption we are making here is that the presentation set does not have any identities that are not already there in the reference set. And therefore, we are going to kind of avoid the difficult challenge of setting threshold on these distances. Right? So this is why we are just picking the shortest distance of the reference image as the predicted identity. And then what we do is we repeat these steps 1 to 3 a number of different times, and then calculate the average identification rates for each of the race and gender groups. Okay, so this is a key step, and I'm happy to further clarify if I haven't been able to explain this clearly. So now we are looking at the identification rates for different off-the-shelf models. So the first model that we are looking at on the left half of the image is the FaceNet architecture from Google. So this is in fact one of the only off-the-shelf models that is been already using the triplet loss. So it is potentially the one that could have the least bias, but indeed, even with that, we see how. So just to kind of quickly see how we interpret these values. So what these numbers are saying is basically that if you are an Asian female, you only have a 65.4% chance of being correctly identified. Okay, so among the 100 different identities that we had in the validation set for each of these different groups, these are the average identification rates. So these are success rates, average success rates for identification. And these tables have all been sorted from the lowest to highest identification rates. So on the right, we have the ResNet architecture proposed by the researchers from Microsoft as a comparison. And what you see from both of these is that on average, females tend to have much lower identification rates as compared to males. And specifically with respect to with respect to race, we see that in all cases that the whites are by far the best performing race compared to the others. So this is a very common theme with respect to both these models. And on the next page, I have 2 more other off-the-shelf models that we have used under the exact same validation setting, and here are the rates. So in terms of absolute numbers, it is the VGG architecture that has the really small numbers, whereas the other 3 architectures have actually very similar absolute numbers. But in all cases, we see this common theme of females doing much worse and white race having much better performance relative to other races. So basically, if you're a white male, you're clearly have the best chance of being correctly identified. And if you are an Asian or a Black female, you have the worst chance of being correctly identified. So this kind of completes our step, the first step that we wanted to do of establishing that there is significant bias in commercial facial recognition algorithms. So we have tested 4 different architectures which have been shared in the open source with pre-trained weights by the original researchers who developed these models. Okay, so what are we going to do next? So the next step would be to now see, do these bias numbers, does it increase or reduce or just remain the same if we retrain these models or tune these models using our triplet loss function by retraining them on different compositions of training data. So what happens if we, let's say, tune these models only on, for example, female images? Do we see this imbalance between males and females reducing or not? Similarly, across race, what if we just tune these models just on a particular race? Do we see these bias numbers or these the bias in the identification rates changing? Right, so that is something that we are trying to do right now, and we are quite excited to see what happens from these experiments. And thank you so much. And what I would love to hear the general feedback from this group on, do you think this approach we are taking makes sense? Would you do something differently, or any other questions or comments that you have on what I've spoken about so far? So thank you so much.